remove the solid, one thing that we need maybe to figure out is what are the sizes of those solids. If you want to use a screen drum filter, I might wonder, how do you know which screen size you should use? A 90 micron, 60 micron, 40 micron? How did you choose the number? Long time ago, I was having that question when I was doing my PhD job, like 25 years ago, more or less. So we just picture something like this. You might have your effluent water with, let's say, that distribution of your particle solids, and you might have another effluent water having that distribution of your particle solids. If you choose a given screen filter that will be this pore size, that means that then in that effluent will be releasing that kind of solid, but in the other effluent tank, you will having that releasing of solids. I mean, in one system, you will be catching pretty much most of the solids, but in the other system, most of the solid will be given out. So how do you know that? How can you do a good selection? Well, back then, we decided to do something that will be cheapest to do, because right now there are machines that you can put with your samples and will tell you the size distribution. But what we did, well, those machines are about between $20,000 to $40,000. You want to have one of those. But it's much cheaper to us if we were doing screens. So actually we do this, a lot of series, a lot of those screens were different sizes. Similar sizes that most of the manufacturers have for their devices. So we have, let's say, from the size of 2,000 micron up to the size of, let's say, 10 microns. So we have all those different sizes, and what we're doing, we capture the solids that you have in the tank, that's in the tank, and then we put the solid in the 2,000 microns, and all the solids that were retained, we knew, oh, those are higher than 2,000 microns. All the solids that passed, we put those solids in the next screen, and let's say it was a 500 micron, and again until we get to the 20 microns, and the final one, we filter into the fiberglass 1.2 microns one. So then we have the mass, and we can calculate the fractions, and then we can also have an idea what is the size of distribution of the solid that we have. So we did that with red abalone. We were doing in Chile also a huge industry with producing red abalone and also the green abalone. We did that research. We got those graphs for those. So these are solids. You can see the percentage between the solids that were between 500 microns and 2,000 microns. They were about 25% of the sample. Between 500 microns to 200 microns, they were about 40% of the sample, and so on. With this, we built this graph here. That actually we were just an accumulation of those percentages, and we did this curve. And looking at the curve was quite easy, just as a first approximation, which kind of diameter of the pore size for a screen device would be needed to remove a certain amount of solids. So let's say here, if we use a 500 micron device, we will be able just to remove the 20% of the solid. If we use the 200 micron, we will be able to remove 60% of the solid. And then if we use, let's say here, the 100 micron, about 80% of the solid. But any other screen that is lower than 100 micron will not increase the efficiency of your device. So no need to go to a smaller screen. So right now we can say that because we have the solid, so we know what we have. But before that, you are just guessing. Same thing we did with the abalone. We were wondering, what if we change feed? Because the abalone, we fed them with seaweed, but back then we were trying to feed them with pellets. So there were companies providing those pellets. And we were thinking, if we change the feed, the particle size will also change. And what about the size of the animal? Is there a small, medium size, or large size? The particle will change, will remain the same. Actually, everything changed. So we were giving them series. They were the curve that we got for the three sizes of the abalone, pretty much the same curve for the small, medium, or large size of abalone. If we look here for a 90 micron screen, that will remove 80% of the solid. But if for the same farm we change the seaweed to this brand or better back then, the distribution change, and also your screen device will change as well. If we move it to the outfit and other pellet or screen that we're also filling, all things will change again. So meaning if you already have a system that is already working with a given screen device and you change your feed, your efficiency for removal solid will change as well. How much will change? I don't know. It depends on the feed that you are providing, and also if your animal is small or medium or large size, that also will change as well. So that's the thing that we learned with the abalone back then. Another research that we were doing also was then moving into Atlantic salmon. Well, I don't have much time to do a lot on my talking here, but we did exactly the same. We were, in this case, we sampled solids for feed that were fed with a pellet at 2 millimeters. The feed were about 60 grams, average size. The density was about 28 kilograms per cubic meter. And the other one here was, they were fed with a bigger pellet because the fish also were big, 156 grams average size. And also the density was quite similar to the next one. But you see, the distribution of the sizes of the solid are not the same either. In this case, this farm, they had a 90 micron screen, meaning that is, this solid were going through that screen, they will be able to remove 55% of the solid. But in this other case, they will be able to remove even more, 75% of the solid. So things change as well. So we were learning about that, and we were saying, oh, that's amazing how your device is changing depending on the size of the fish and also depending on the size of the pellet. Something today care about the fundamental where you're looking how to remove particles thinking on the size. But what about when you do sedimentation? How do you choose or design your setting device? Well, particles in aquaculture, they not settle all at the very same time together. Anyone has two pieces of sheet paper here that can lend me? I need 2 pieces of papers. That to have a very fast demonstration. Oh, thank you. Well, kind of similar. Which you will say, which is the density of this paper and which is the density of this one? Are the same or they're different?
Same.
Are the same, isn't it? So is they are the same, let them to fall, which one will be reaching the table first? More or less the both, we see. But what about if I do this? Which is the density of this one and which is the density of this one? Same again. Which one will be falling first? So that happened in aquaculture as well. Same thing. Same thing. So what I'm trying to do here is that we have a stop law that is trying to explain how the solids will settle. But the stop law was done with spherical particles. In aquaculture, our particles are not spherical, as you can see on that cone. They have different shapes, and also, depending on the shape, they will have different velocities. So how do you estimate then which is the velocity? So far, I will go into some theoretical thing first regarding setting devices. This thing you can find it in any of the books that I showed you before. They basically explain how you get into a parameter that we are going to use. So you might calculate the horizontal velocity just using hydraulic formulas, like that one. Then you can use also the Stock law to determine which is the vertical setting velocity. So we will have this device right here. And you suppose that the particles that will follow that trend will settle. So any particle that will be in this part of the area will settle in the device. Any particle that will be in this area that will be getting out of the device. So that basically the theory is telling us. So how can we approach